lecture is chapter 7. This is where we have stopped this morning. And we already defined this time constant tau. Larger tau means longer transition time, and shorter tau, small tau means shorter transition time. And its physical meaning is for certain initial voltage value, the larger the capacity you have, the more energy you can store. And the larger the resistance is, the smaller the discharging current you have. So you have if you have a large resistance and a large capacity, so when you storage a lot of energy, but you can only discharge it through very tiny discharging current. So which is not which that will causing you extra time to do so, like this. Big tau. So this is the meaning of tau. So this is a physical meaning of this time constant tau, and we can see it from the output of the voltage of the capacitor. When our time through 1 tau and 2 tau, 3 tau, 5 tau, our output voltage will decay from UO to UO e times minus 5. With respect of minus 5. And you can see the number of it. Number will drop from 1 UO to almost a third of UO and to almost nothing. So we see that we can calculate that, and we can also measure it. So in reality, if we are in practice in the factory, and we would like to know this time constant of a system, we can test it, and we can tell it from the output curve. We can just measure when the capacitor voltage decay to 36.8% of the original value. So then we mark that time. Then we have this number of the time constant, but this is only for this first order linear system. For higher order, and we have different methods, but the basic thinking are almost the same. So let's see, nothing particular. So now we can we see that how to do it and how to measure it in practice. You measure this value, then you will have the number of it. Not only for our circuit, and in other similar process, we can still measure their corresponding tau. So the time constant is not restrained to this domain. It is very widely used in many physical surroundings. So, and let's see the geometric meaning of the time constant tau. We know that the slope of the curve at T1 is equal to this formula. So we can so for T1 we have this value. So T2 we have this value. And the slope of the curve at T1 is equal to this stuff. And tau equals to T2 minus T1. So it's actually the distance between T2 and T1 on the time axis. So it's the length of the secondary tangent. Oh my god. Wait a minute. Okay. For well, my signature, my signal is not very good, but I think that's okay now. Let's see. So this is a geometry meaning of the time constant. So this is a y is equals to 0.368. You see. So let's see it from the energy relationship. Let's see. In this circuit, the capacitor acts like the giver, and the resistor acts like the taker. And the capacitor continuously releases energy, and the resistor absorbs the energy until all the electric energy is completely consumed and turned into thermal energy, into heat. So we can say that you see 0 plus equals to UO, and the energy released by the capacitor is half of the C UO square. And we can see the energy absorbed by the resistor. We can calculate it by using this integral. So we know that I squared times R is the power, and the power's integral is the energy. And we know that I equals to O over R equals times E with respect of minus T over RC, and this one square. So we do this integral, and still we have this conclusion. Then we see that those two are identical. So all the energy is consumed by the resistor, and completely. So let's take an example. Let's see. Voltage on the capacitor, and once we close the switch, and we would like to know the current voltage on each branch, and how they changes. So let's see. Still, this is a typical problem of acquiring the first order zero input response. So we can use the conclusion we have directly. So this is RC square, and we can just turn it into a typical RC square. First order RC square is a resistor seriously connected with a capacitor, right? So it will turn into like this one, and we can just directly using the conclusion we have. So using this stuff, and we know that UO equals to 24 volts, right? 24 volts. So we can see that tau equals to R times C. So C is 5 farad, and R is 4 resistor, so it's 20 per second. So we know the value of UC, and then we could know the value of I1, and so on and so forth. So instead of doing the traditional way of list the first order differential equation to solve this problem, we're using the conclusion of the typical RC circuit and deal with it directly. So we use the conclusion. So this is how the engineer solve this problem because this is much more efficient. Let's see another example. So let's see, we have a circuit look like this, and we have the original value of the voltage of those two capacitor, and they are in a parallel in a series connection, and we would like to know once we close the switch and the current I. So this is a okay, not very okay. Should put it down. Okay, this one is too close to the text, right? So we would like to know how the current and the voltage changes according to time, and we would like to know how much energy is stored in the capacitor, and the final energy stored and the energy consumed by the resistor. So let's see. First thing first, we know that from energy conservation theory, we know that all in this circuit, all the stored energy will eventually consumed by this 250 kilo ohm resistor. So anyway, we will just do it. It's still a typical RC problem, and we can turn it into the typical RC circuit. So those in the series connected capacitor, we can just put it, change it into a equivalent capacitor. So we know we can replace those two with one single capacitor, 4 mu farad capacitor, and we know that since those two capacitor have a different they have an unassociated reference direction, so their total voltage will be equals to 20 volts. So because they have unassociated reference direction. So we have this stuff. So we can just directly using the conclusion we have for the RC square. So tau equals to R times C, 250 times 4 times 10 to with respect of negative 3. So the tau is 1 second. And U equals to 20 times E respect of 2 negative T. So the current is like this. And we can calculate U1. U1 equals to U10, and U10 we already have, right? U10 is 4, and we can do it like this. Since its reference direction is different from the other one, so it's different from the equivalent capacitor. So we give it a negative 4 volt as the initial value. So the other one is 24, and by doing this integral, we can calculate how it the voltage changes. Let's see what's the problem. What's the problem? Irfan Haider. Uh, so let's see the initial energy storage in this. So we can just directly using this equation. So what's your problem? Irfan Haider, what's your problem? What would you expect to say? Okay. If you have nothing to say, so we continue. Uh, I don't know. I think I have a 90% of chance to misspell your mispronounce your name, but anyway, anyway, you can understand it. So let's see the final energy storage, and we can just come together. So it's 500,000 millijoule. And the resistance energy consumption, you can see, it's like this. So let's see in this example, we calculate it using the equivalent reference equivalent capacitor. But honestly, we would like to calculate the energy. The energy could not be calculated like this. So we see energy have a different expression. Actually, this one should be that's one. Anyway, it doesn't matter. So let's see the zero input response of a resistor, conductor, resistor inductor circuit. So let's see, we have a circuit look like this, and at time zero, we close the switch. So let's see what happened in this circuit. So we know that the current of the inductor cannot jump. So we know it will remain the same before and after switching, and before we close the switch, inductor actually behaves like a wire, because in the steady state of DC circuit, it works like a wire. And we know that we can see I see over larger than zero moment, then we see that we actually disconnect the two parts of the circuit. So we can calculate the corresponding value of this circuit only. So we can list the equation for this circuit. It's from its VCR and this is a KVL. What's the problem? Let's see. Very annoying. Okay. Who's that? I didn't accept you. I don't know. Never. I don't remember that. Okay, let's continue. Let's see. So we know we can list this like this using the VCR. So from the first order differential equation knowledge we have learned from the calculus, and we know that this characteristic equation could be look like this, and the eigenvalue will be P equals to negative R over L. So we can write the corresponding L like this one. And the initial value of the L we already know is like this. So we can just put it in and we'll reach the conclusion. So this is it. It looks very similar to the RC circuit we have talked about before. So we know that inductor and capacitor, they are a dual. So their response in this similar circuit looks very similar. And this the current is changing according to this equation. We can calculate the corresponding voltage. So we see they are the same. They are decaying with the same exponential rate. So their time constant is still the same. So we know that the voltage and current are functions of the decay of the time according to the same exponential law. So their structure, their curve that looks very similar. We feel overflip this on the other side. You can see they almost looks identical. So this is a continuous function, and this is a jump. So we see the current of the inductor cannot jump, but its voltage could. So the voltage just jumps. And we know that the response is linear with its initial state, and the decaying speed is related to the ratio of L over R. So we call tau equals to L over R the first order RL circuit times constant, and the unit is second. So still, this time constant reflects the length of the transition time of the circuit. The large tau, the longer transition time, small tau, the shorter transition time. Let's see the physical meaning is very similar to the capacitor we have talked about. When the current have a certain initial value, so the initial value of the current is certain. If we have a large L, so a large L, which means we can store more energy. So, and a small resistor. Small resistor means the energy consumed in the discharging process is smaller. So we know that the power of the energy consumed by the resistor is equal to R times the square of current. And with a small resistor, the current, the energy consumption is relatively small. So you have a lot of energy, and you have only one time small tube to release that. So that will cause you extra time to consume all that stuff. So large tau means slow discharge and means longer transition time. Let's see the energy relationship. The energy released by the inductor is consumed by the resistor until all the energy is burned out into heat. So we assume that the initial value of the current is I/O. The energy released from the inductor is the half of the product of L and the square of I/O. And the energy absorbed by the resistor, we can calculate that. Still, we're using this formula. This is the power, and the power of the integral is the energy. And we can calculate it like this. And still, the same number again. So all the energy released by the inductor is consumed by the resistor. So the resistors are pure consumers, and the inductor, the capacitor, they are storer. So they could only store energy, but they cannot consume them. Let's see an example. At time 0, we open up the switch, and we would like to know the UV number, the value of the UV. So the voltmeter range is 50 volt, and we would like to calculate that. For ideal voltmeter, it looks actually behaves like a open circuit. So let's see. Original state of the current IL equals to 10 over 10 is 1 ampere. So for its from a steady state, it looks like it behaves like a wire, right? We already know that. And we know IL equals to this stuff. From the conclusion, we have already write about it, the IL circuit. And we know that the tau equals to L over R. R equals to consists of two parts. One is L, the other one is RV. And since RV is 10,000 and R is 10, so it's too much, so we just neglect it, so we can have a right, almost right conclusion. So we know the voltage of it. Let's see. Let's see for the ideal voltage source. It will be look like open circuit, but actually in this case we don't see that. So it's 10,000 plus 10. We in order to save the labor in calculating the numbers, so we just omit the 10 ohm resistor. So we have this stuff, but it's almost very close to the real accurate number. And we know that UV times 0 plus equals to negative 1000, like this one, from this, and it will cause damage to the voltmeter, because voltmeter only can stand 50 volt voltage. So you put 10,000 volt on it, it will break. So sometimes we put a diode in it to form a continuous path for the inductor to release the energy once we turn on the switch, turn off the switch. So will cause a continuous loop to burn out the extra energy stored in the inductor. Let's see another example. At time 0, we switch the switch from port 1 to port 2. So I would like to know the value of the current and the voltage of the inductor. And I would like to know the voltage between the switch U1, 2. So we still use this knowledge we have learned from the moment 1. We connected with switch 1, so it forms a path like this, and the voltage, the inductor works like a wire. So 2/3 of the current runs through this branch, the 1/3 runs through this branch, 1/3 of the and 2/3, and so 3 and 6 are in parallel, and 4 and 2 they are in series connection. So 4 plus 2 plus over 24 is a current, and 2/3, 6 over 3 plus 6, so it's 2 ampere. So it's very easy to calculate, and once we know the original number, and we can calculate this corresponding current. So we could transform the we can say the equivalent R equals to 6 ohm, and see that 3, 2, 4, 6, those 2 plus 4 and 6, they form a parallel connection, and 3 forms one connection to the main connection of it. So the equivalent resistance equals to 3 plus 2 plus 4 parallel with 6, so it's 6 ohm, and the number of the inductance is 6 Henry, so it changes into this form, and so we can apply the conclusion of this RL circuit directly. So tau equals to R, L over R is 6 over 6 is 1 second, and we can calculate the corresponding current like this, and this is corresponding voltage. So it's once we have done with it, we can calculate the voltage difference between 0.1 and 0.2 is 24 plus 4 times half of L. So this is since half of L runs through it, so this is a U12, and we see that they share the same point like this. So we know the difference between them. So let's sum it up. The zero input response of the first order circuit is caused by the initial value of the energy storage element. So zero input response is the response to the residual energy stored in the energy storage component. So it's all decaying, exponential function decaying to zero. And for RC circuit, we know that the voltage of the capacitor cannot jump, so we use this, take advantage of this feature. And for RL circuit, we know that its current cannot jump, so we take advantage of it. And the decay rate, how fast the decay happens, depends on the time constant. For RC circuit, tau equals to the product of R and C, and for RL circuit, tau equals to L over R. So we only have to remember that. And R is the equivalent resistance of the one-port circuit connected to the dynamic element. So if we would like to calculate the corresponding R, equivalent R in this circuit, we only have to transform the remaining circuit into the typical RC typical RL structure. Then we could calculate the corresponding equivalent resistance and all the equivalent capacitor and equivalent inductor. So we see that within the same circuit, all response have the same time constant. So they all decay with the same exponential rate. And we know that the initial, the zero input response of the first order circuit is proportional to its initial value. So we call it zero input linearity. So this is something we should know. Now we can move on to the so-called zero state response of the first order circuit. Zero state response of the first order circuit is completely different from the zero input. We see zero input circuit, there's no extra power supply in the after the switching. So all the circuit runs on the storage of the energy storage components. So once that energy is gone, the circuit is dead. But the zero state response of the first order circuit is completely different. Let's see the definition of the zero state response. When the initial energy stored in the dynamic elements is zero, and once we put a power supply to the circuit, and all the response generated by putting this power supply into this circuit is called the zero state response. So zero state means the storage in the capacitor and the conductor of the circuit are zero, so they are in a zero state, zero storage state. Let's see the zero state response of the RC circuit. Here we have this one, RC and EOS. At time zero, we close up the switch and we can skip value. So the differential equation, we can list it like this. We are very familiar with this first order differential equation, and we can just that is still a time invariant coefficient differential linear differential equation. So long. That name is so long. We can derive the result into two parts. Still, the general result solution and the special solution. So the special solution of this non-homogeneous equation is actually what we talking about in this lecture. And the general solution of the homogeneous equation is what we talked about in last lecture. So you see, dot is called the special solution. It's also called the first part. So the special solution for this first order differential equation, could say that you see dot equals to US. So it is so-called first part of special solution is forced by whom? Is forced by the external power supply we put into the circuit. So its special solution is caused by this power supply. And it is related to the variation of the law of the input excitation. And it's a steady state solution of the circuit. So this is the compulsory part, or the first part. And the UC2 dot is called the general solution, the free component or transient component. It's the general solution of this equation. So this solution, the general solution, its variation law is determined by the circuit parameter and the structure of the circuit. And the total solution is a combination of two. Well, we don't usually encounter a completely zero input system or zero state system. This is rare. Sometimes we generally equals to we often encounter a system that both have initial condition, but and also compulsory response. So we add them up together, a special solution and the general solution, and so this is it. So from the initial condition, you see 0 plus equal to 0, we can calculate the integral constant a. And we know that UC 0 plus equals to a plus US equals to 0, and so a equals to the minus US. So we can rewrite it like this. UC equals to US minus US times E with respect to negative T over RC. So from this equation, we can conduct that I equals to C times the differentiation of UC to time T, and we can rewrite it like this one, US over R times E with respect of minus T over RC. So this conclusion shows what we know that the voltage and the current still a function that changes with time according to the same exponential law, and the voltage of the capacitor also contains two parts. Let's see in this figure, the compulsory part or the first part is actually caused by the power supply. So the source gives its energy and force the system to work on its will. The other part is a transient component, the free part component. So those parts combined together will generate a full response or total response. Looks like this is the right one. So it's a continuous function. And the current, you see, in this circuit circumstance, it has a jump. Still, this is what we're talking about. So now we see that the special solution corresponding to the response generated by the source, and it's also called the compulsory response. The general solution of this differential equation is the free response. So is influenced by the structure of the circuit. So this is it. And we know that the speed of the response is determined by the time constant. And we have two different set of tau. One, the RC 电路RC circuit is the product of R and C, and in the inductor circuit is L over R. So we see that the larger tau you have, the charging process will be slower, and the smaller tau you have, the charging is much more rapid. And we see that the response is linear with applied excitation. So this is a linear system. And let's see the energy relationship. The energy relationship is very simple. We see that part of the energy is consumed by the resistor and burned into heat. The part of the energy is stored in energy storage component. So the energy from the source we can calculate is US times I, and the integral from time 0 to infinite. So it equals to C times the square of US. And the energy is consumed by resistor, we can calculate it like using the square of I times R, the integral of it, and we still have it. And the energy stored by the capacitor is half of this. So we see those two combined equals to the total energy provided. So we see half the energy provided by the power supply is consumed by the resistor, and the other half is converted to electrical magnetic field energy and stored in the capacitor. Let's see example. Let's take a 10 minutes break.
再有机会在这边跟大家一起共度这个蒲公英爱情蒲公英的演唱会，好不好？但是在下一次的聚会之前，我希望大家可以珍惜今天晚上最后的机会，大家能够跟我一起合唱。 在乎你心里还有谁，且让我给你安慰。不论结局是喜是悲，走过千山万水，在我心里你永远是那么美。既然爱了，就不后悔。再多的苦我也愿意背。我的爱如潮水，爱如潮水将我向你推，紧紧跟随。爱如潮水，它将你我包围。我再也不愿见你在深夜里买醉，不愿别的男人见识你的妩媚。你该知道这样会让我心碎。答应我，你从此不在深夜里徘徊，不要轻易尝试放纵的滋味。你可知道这样会让我心碎？谢谢。既然爱了，就无怨无悔。再多的苦我也愿意背。听你们唱。爱如潮水将我向你推，紧紧跟随。爱如潮水，它将你我包围。我再也不愿见你在深夜里买醉，不愿别的男人见识你的妩媚。你该知道这样会让我心碎。我你从此不在深夜里徘徊，不愿轻易尝试放纵的滋味。你可知道这样会让我心碎？我再也不愿见你在深夜里买醉，不愿别的男人见识你的妩媚。你该知道这样会让我心碎。答应我，你从此不在深夜里徘徊，不愿轻易尝试放纵的滋味。你可知道这样会让我心碎？爱如潮水，谢谢，谢谢，谢谢。
Very popular his song, and but he died in a car crash, and many years ago, it's about 20 years ago. I think almost that long. So this is it. Now, okay, let's go back to our lecture, and let's see this example. And we turn on the switch. We close the switch at the moment 0, t0, and we know that the originally the value of the the voltage on the capacitor is 0, and we would like to calculate the voltage and the current of the capacitor, and we would like to calculate the time t for UC to reach 80 volt. See this the source value is 100 volt, so we would like to know when will this stuff reach 80. So this is it. Okay. So let's do it. From the precognition, we know that it actually is a zero state response issue. So it's very simple. We know that there's only one resistor, one capacitor, so its time constant RC equals to 5 times 10 with respect to the negative 3. And we can write it directly like this one using the conclusion we already know that, right? So we just directly put the corresponding value in, and then we will just so US 100 and this one 200. So we just put it in, then we'll have the conclusion. So we don't have to painstakingly do the calculation. And the corresponding current is like this. Okay, and now we can we already calculate the corresponding voltage and current of the capacitor, and we by solving this problem, we put 80 volt in, so we can reach the time. So time equals to this. So this is a very typical example of how to apply this stuff. So once we encounter this stuff, this kind of a circuit, we can using the conclusion directly, and we just the only thing we would like to calculate is the corresponding coefficient, like the time constant tau, and the initial value US, and we just put it in, and that will be all. So it seems very easy. Then the previous example we have give you in the former lectures. And let's see, the zero state response of the RL circuit is very similar to those the RC circuit, right? So still we have this kind of a circuit, a series connected resistor and inductor and voltage source. And we know that at the very first moment, there's no current in the inductor, so it does not contain any energy in the first place. And we use the KVL and the VCR to release this first order equation, and we can calculate it like this. Still, we can divide the solution into two parts: the special solution and the general solution. And we know that since L times 0 plus equal to 0, since this one, and know that the current of the inductor cannot change, so it must be equal to 0. So we can have this this coefficient A equals to minus US over R. So we can rewrite it like this. So we now know the current, how the current changed for this circuit. And we see, we have the current grows, increases exponentially, reverse exponentially to its final value. And since we have already know the current value, we can calculate corresponding voltage value, and is still is according to the exponential law. So the voltage and the current, they share the same time constant. So they share the same shape of exponential law. So very similar to that of the conclusion of the capacitor. So let's take an example. See, in this case, we have a inductor and connected with many resistor and current source. And at time zero, we open up the switch. We would like to know how the current IL and the voltage UL changes when T is larger than zero. So once we turn on the switch, then the current source will no longer be short circuited. So the current will run into the rest part in the pink square part. So that will generate a corresponding response. Let's see. This is a typical RL zero state problem. So we can first we have to simplify the circuit into the typical RL circuit. So we know those two in parallel and series connection with it, and this one and those two are in parallel connection. So R equals to 80 plus 200 and 300 in parallel. So this path is actually a typical RL path. And we know that then we can simplify this into this one. And we can calculate the corresponding tau and the corresponding we know that eventually the current will reach 10 ampere, and because this stuff behaves like a wire eventually. So in this loop, there's only the equivalent resistance and the inductor. So we know that eventually it will bypass the equivalent resistance. So we can calculate the corresponding IL and the corresponding UL. So this is it. It's very simple. Now let's see. Take a look at another example. And we can see that we would like to know how the IL and the UL changes according to the and the voltage of the current source how it changes when time is larger than 0. We know that at time 0 we open up the switch K. So yes, this switch we see that still we have to transform this circuit into a typical RL circuit. So we see that you see this 10 and 10 plus those two of this part is from the a typical RL circuit. So we can calculate the corresponding equivalent resistance. And we know UO equals to 2 times 10 is 20 volts. So we could transform this into this equivalent source. And we know that the tau equals to L over R EQ, so is 0.1 second. And we know that eventually R must equals to 1 ampere, so it will behave like a wire eventually. So we can calculate this. We can just put those stuff into the conclusion we have, and then we have the final result. And once you know the voltage, and you can derive do the differentiation of it, and then we will reach the voltage, and it will show as this. So we can calculate those stuff together, and we can combine them using this conclusion, and to calculate the original circuit. Then we can calculate the corresponding U. So those examples are not very difficult to solve, and the only thing we have to calculate is the equivalent resistance and the corresponding times constant, and the initial condition. So we just put them together, and we'll put it into the conclusion, the general solution form. Then we have the result. So it's not very difficult. Let's see the total response of the first order circuit. We know that total response of the first order circuit is consists of two parts. The response, we know that for this circuit, we assume this initial state is not zero, and in the meanwhile, it has the extra stimuli, extra power supply to stimulate the circuit. So its total response, the full response, for example, for the RC circuit, the total differential equation could be listed like this, right? And the answer still could be divided into two parts. A special solution US dot equals to US. The general solution US 2 dot equals to A times E with respect to negative T over tau. Tau equals to R times C. So we can calculate the coefficient A from the initial values. We know that the voltage UC 0 negative equals to UO, and so we know that UC 0 plus must equals to A plus US equals to 0, U0. So we know that the coefficient A equals to UO minus US. So we just put it in, we have this final conclusion like this. So once we have this this kind of a problem, we just calculate the corresponding tau, and we calculate the corresponding UOUS, and we just put them in. Then we'll have the final conclusion. And the first part is called the compulsory, the first component, and it's actually the steady state solution, and the other part is called transient component, or the free component. So it represents the part that will decay with time, within time, and will just gradually disappear. So we can see the two kinds of decomposition method of the full response. We can focus on the two working states of the circuit. So the total response equals to the force components plus the free components. One is a steady state solution, the other one is a transient solution. So the pink line is the steady state solution, and this blue part is the transient solution, and we can combine them. So we have the total response. That's the response of the red one. So it actually contains two parts. So it has a very clear physical meaning. Of course, we can causality. So we focus on the cause-effect relationship. So we still can divide it into two parts, the zero state response. So we can see that the first part is the compulsory component. The first latter part is the free component. It's the first classification. The other method is to divide them into two parts. So the first part is a zero state response, and the other part is a zero input response. So once we would like to calculate the total response or the full response, we can divide it into two parts. We can calculate the zero state response, and we can calculate the zero input response, and we put them back together using the superposition theory. We can have the same conclusion. So total response equals to zero state response and zero plus zero input response. For example, we can just put it, divide this, see, we have zero state. And this time we just divide it into non-zero state with a zero state. So this is a zero input, and this is a zero state. Those two combined to be the total response. So this is how we define them. So it's very convenient to do the superposition calculation. But as we all know that for superposition calculation, we have some special case to consider, that especially when we encounter the control sources. So if we encounter those kind of sources, we better take care. And still we can see this two parts, zero state and zero input. And we put them in the diagram to see that this is the zero state response, and this is the zero input response, and we combine them together. Still, we have this full response, total response. So let's see an example. At time zero, we open up the switch key, and we would like to calculate the corresponding IL and UL after time zero. So we can do it in two ways. We can divide them into two parts, zero state and zero state, zero input. And we also could do it with the compulsory and the free component. So this is a typical RL circuit total response issue. We know the current will not jump, so the current originally will be 24 over 4. Since before time 0, this loop is connected, and this one is actually a wire. So it's 24 over 4 is the example. And the tau is L over R. L is 0.6. And after we turn on the switch, so this 8 ohm resistor is back in the circuit. So the total is 8 plus 4, 12. So we have the tau. And the zero input response, we put them together like this one, L dot. And the zero state response, we put them in, is this one. And we add them up together, then we have the total response. Simple as it is. So it's too simple. We just calculate the corresponding value, parameter value, and we put them in. Then using the superposition, we add them up together. Then we have the full response. So it's very useful when we're dealing with this kind of a scenario. Of course, we can calculate the steady state components. Infinite equals to 24 over 12 equals 12. And still, we have this total response, like look at this. And we also could substitute into the initial value. Look at this. So anyway, you can do those two method both are right, and that will reach the same conclusion. Let's see another example. At time 0, we close the switch K, and we would like to know the value of IC and UC of the capacitor, and the voltage of the current source. So we know that UC 0 negative is 1 volt, and the capacity is 1 farad. Actually, it's a very large number, but anyway, for the case, we just omit that. So this is a typical RC circuit total response issue, and we can calculate the steady state components. You see, infinite is 10 plus 1 equals to 11 volt. So once we close it for a long time, it will be a open circuit part of the valve. So it means its value equals to 1 ampere running through it, and plus 10, so it's 11. And tau equals to R times C. C is 1, and R equals to 1 plus 1. So in this case, this one does not react. No, sorry, this one does not react. Because no matter what, the current runs through is still 1 ampere. So and we can see that the total response is 11 plus A times this stuff. So let's calculate the A. So we can see that 10. So we put it in, and we have the UC and SC. And the UT, we have we only need to use the KVL to solve this. So the Kirchhoff's voltage law, we can reach the conclusion. So it's very simple for this case. Now let's see the 3 factor method to analyze the first order circuit. We know that the first order circuit is a mathematical model is a first order linear differential equation. Look like this. So we have A, B, C, 3 coefficients. And the answer, the general answer is look like this. Ft equals to F dot T is the differentiation of Ft plus A times this stuff, blah, blah. And we see that let T equals to 0 plus, and F0 plus equals to F dot T 0 plus A. So A equals to F0 plus minus F dot T at the value of 0 plus. So Ft equals to this stuff. And with DC excitation, we know that Ft F dot T equals to F the differentiation of a constant is a number, right? So it equals to F infinite. So it looks like this. Ft equals to F infinite plus F 0 plus minus F infinite. So we only need to know the value of F infinite and the F0 plus. So F infinite is steady state solution, and F0 plus is the initial value, and tau is time constant. So once we figure out those three numbers and we just put it back into it, then we have the final conclusion. So we can use the steady state circuit to solve, then we reach the F infinite, and we use the 0 plus equivalent circuit to solve the F0 plus. And tau is a very easy. You only have to distinguish whether it's a RC circuit or is a RL circuit. So we can use we can transform this first order circuit problem into a problem to solve the three factors of the circuit. So we have another way to solve it. So let's take an example. We know that at time 0, we close the switch. We would like to know the voltage of the UC after switching. And before switching, we see that the voltage on this branch is actually 2 times 1 is 2 volt. And after a while, we see that the voltage on it will change. Will be 0.6.6. Since this is 1 amp, this is 1 ohm, this is 2 ohm resistor, and they share the same current. So the total equivalent current on this one is 1/3. So it's 1/3 times 2 ohm is 0.66667. So the equivalent resistance is equal to 2/3, and because this 2 ohm and 1 ohm, they are in parallel connection, and so their combined resistance is 2/3, and the capacitance is 3, so the tau is 2 seconds. And now we have UC0 plus UC infinite and tau, and just put it in. Okay, so we have UC. Oh, almost that simple, right? Just that simple. Let's take another example. Let's see another example. When time 0, we close the switch. We would like to know L, the current through the capacitor, the inductor, and the voltage, the current I1, and the current I2. This one. After time 0, so still we can calculate it. Three factors. We know that before switching, the current in this loop, this is actually a wire, so it's like this one. The 10/5 is 2 ampere. And after we switch this stuff for a long time, still we have two loop connected. So it's 10/5 plus 20/5 is 6 ampere. So its the initial value and the final value is known. Now let's see is the time constant tau is 0.5, and those two are connected in parallel connection. So we can calculate the tau. So we just put him in. Okay, then we have L. Then it's very simple to calculate the other two. UL we have the UL, and 10 minus UL over 5 is this one, I1. The other one is simple, 20 minus this one, and over 5 ohm is the I2. So we now know the value of IL, I1, I2. The three elements we can calculate like this. So this is it. Let's see another example. When we switch the switch from point 1 to point 2 at time 0, we would like to know the UC value after switching. So before switching, we know that the voltage on the UC must equal to 8 volt. Once we close it up for long, this loop is actually a acts as if it's been opened up. So there's no longer any current run through it. So the value is 2 times 4 is 8. Oh, I almost forget about that. Full 1 and 2 ampere. Okay, it's 12. Once we close it up, we still have this circuit, this one. Okay, we still have this one. I forget about this one. So don't forget about the control source. So you can calculate this stuff, and you see infinite is like this one, and U equals to 10 I1. So we can calculate the corresponding equivalent resistance U over I1 is 10. So we calculated the equivalent resistance. Now we can calculate the corresponding tau. So the corresponding tau equals to Req times the capacitance. So we put them together into this standard equation. Let's take another example. So we have many examples. Otherwise, the theory is not very easy to digest, but combined with the examples, I think you can digest it. Let's see. For this example, for example, we know that in this case that after time 0, we close the switch, and we would like to know the current IT after switching. IT is a current run through this branch. So before we close it up, the value of IT is 0, and after a long time, we close it up. There's no current run through this branch, and the steady state of the current is after a long time this inductor behaves like a wire. So the final value of it is 10 over 5 is 2. So, and we know that for this capacitor, its original value before we close it up is 10. So this open circuit, and after a while, once we close it up, it will be 0. So, and for this loop, is 2 times 0.5. So for this loop. And for the inductor, you can see that original value is 0, final value is 2, and L equals to R over Req. Req is 5 because we don't have this loop. It's been short circuited, and so we don't have to worry about that. So it's 0.2. And we can calculate the UC. We put them in this. So, and L, we just put them in this. We see the number of it. They don't share the same time constant. And IT equals to this. So we see IT, it contains two parts. And this one is this. They don't have the same time constant. So this is a very special case. So once we using this three-factor method, we can calculate this stuff. The special place of this example is it contains two energy storage components. So in general, actually is no a first order circuit, but by applying this three-factor method and applying the superposition theory, we just divide it into two, the combination of the two first order issue, and we put them we put the together back together. So this is how we solve it. And let's see another example. See. In this case, we say that there's no energy stored in the inductor in the first place, and at time 0 we closed up S1, and at time 0.2 seconds we closed up the second switch S2. So we would like to know the current IT runs through this the inductor. So we can see that the initial value of it is actual. We can divide it into two parts, right? From time 0 to time 0.2. So in this case, we can still use this three-factor method. We know that originally it has no initial value, and the current of it is 0. Tau equals to L over R. R is 2 plus 3. So L is 1. And did I wrote it down? No. Okay, I lost it. So this is 1 Henry. Oh. And the final value of it is 10 over 2 is 10 over 5 is 2 ampere. So we can calculate it like this. And the initial value at 0.2, we can put that t equals to 0.2 in this in this formula. We can have the final value of 1.26. So the for the other stage, the I 0.2 plus is equal to this one. So, and in the second loop, once we close it, we bypass the 3 ohm. So the resistor will only be 2 ohm. So it's 2 ohm. So 1 array over 2 ohm is 0.5. And the final value of it is this one. This one is 10 over 2 is 5 ampere. So we put it in. So we have the formation of IT. So we can see this IT actually contains of two parts. Time 0.2 and the time after 0.2. So from time 0 to 0.2 second and from 0.2 seconds to infinite. So it has two parts. It's a sectional function. And we see those two parts contains the different time constant. So we actually change the structure of the circuit, and we change the corresponding time constant. So this example. Now we can see the step response of this first order circuit. Unit step function. The definition is very simple. We put a value of 1 step signal into it, so it's a unit step function. Before time 0, there's the value of it is 0. After time 0 is 1. So the value of 0.0 minus is 0, and the value at 0 plus is 1. So this is how we describe it. And we can talk about the delay of the unit step function. We can do it at any other time. So time till like this. So we could dismember it into two kinds of two unit function combined together. So we can still write it like this. T is smaller than the TO and larger than TO. So how are we going to use this steps function? So we can mimic the action of the switching. So once we, in case, or we would like to talk about the occasion that we have to mimic the action of turn on turn off the switch. So we can put this function in it too. So for example, at time 0 we close the switch. So ut equals to e times et. So this one with the switching action will turn into this one. So we don't have to switch in this loop any longer. So we can we can do it completely the mathematical way, and we can do it like this. So we can at time 0 we close it up. So we can omit the switch and write it like this. So this is what we introduce the unit, the step function in it. So we can just use the mathematical function to replace the oral description of the switch in the circuit. So see, we have a sin t function, and if we would like to cut off some of it, we just put it with times it with this is a sin t times e t minus t0. It's too dark. Okay, we also use this function to delay a function. So this is it. We know that the sin t have many stuff. It's infinite, but if we only want one part of it, we can use this stuff. So we use this function to cut off the function. But when we will gonna meet the sin t, we're gonna meet in the future lecture. So much for today. See you next week. So class dismissed. Are you listening, guys? Irfan Haider, are you listening? So the class is dismissed.